So hi, for those who are listening, watching, I'm Zbigniew Wasilewski, and I'm hosting today's seminar. But let's just maybe wait a couple of minutes before I make a bit more of an introduction. We already have a fair amount of participation, but typically we find that giving another 2-3 minutes allows those who just realized there's a seminar to join in. Welcome to our first seminar in the series of monthly ECE seminars. And as I mentioned during the departmental meeting, our research committee has decided to have 3 seminars per semester, and we will have one from our senior professors and one from junior professor and one distinguished seminar. So today we are starting with very senior professor Krzysztof Czarnecki. Before I go into introduction, I also would like to acknowledge that we are launching these seminars with the help of WIN, Waterloo Institute for Nanotechnology, and Bella Mackenzie is helping us here behind the scene. It's a little bit of a learning curve with this WebEx. I think when it's running, it's all good, but getting it started was a bit of an adventure. So forgive us any glitches should they happen. Okay. So Krzysztof is a professor at ECE, and he is also cross-appointed with the School of Computer Science and specializing in general software development, but really in this seminar he is here as an expert on safety of the autonomous driving, and there was a lot of action under his leadership here on the campus with getting our first autonomous cars on the road.
Right. Thank you, Zbig, for the introduction. Quite amazing. This is the first time I'm giving the talk to the department since my job talk almost 20 years ago. So it's wonderful to have this opportunity. All right. So over the next 50 minutes, I'll give you an overview of the area that I've been working in for the last 5 years, which I find quite exciting. And so I'm also excited to be able to share it with you. All right. So what we're going to do is, I'm kind of prepared a talk that covers this field of automated driving, sort of from most basic questions of what it is, why we're doing this, how we're doing this, and where we are and where are we going. And so I'm hoping to give you some insights into these answers to these questions. We're probably going to spend most on the how, but I believe the whole story is important. And I encourage you to ask questions along the way. Hopefully, we'll have enough time to address all the questions. All right. So let's start with the what. So there's different levels of automation here. I'm going to just focus on the sort of truly automated systems that we sometimes call autonomous systems, where the occupants of a vehicle can essentially relax, if there are any occupants, let's say. So and a good example of that is the Waymo One, which is actually a service that now the public can take in Arizona, in Chandler. It's a suburb of Phoenix. And other examples would be like a shuttle bus, for example, right, where there is not even a steering wheel. It could be delivery vans. So here's a good example is the Gaudi company that's actually testing these vans in Canada, among others. Or for example, trucking. There's several companies that are trying to get into that market. And currently there's really just the Waymo One is a really commercial service with this level, so-called level 4, this full automation. There's also AutoX in Shenzhen, and that's, as far as I'm aware, that's the only real-world services in the world. Okay, so why would we like to maybe do this? And really today, the main driver for that is economics. And so I guess this is an example that perhaps Uber, some years ago, made on the back of that envelope and pitched this to the investors. So if we take something like ride hailing, for example, 50% of it is fuel and vehicle depreciation and maintenance and so on. And then 25% is the cost of driver, 25% is what Uber then takes. And I guess the driver for Uber back then to invest into this technology, and for many in this field, has been essentially to get rid of the driver. But I think for the society, the biggest benefit comes from the potential reduction in injuries and fatalities. And so just, we always have to be reminded that more than 1 million people die on the roads worldwide. And more than 90% cases, the investigations are showing for those fatal accidents that there's been some human error involved. And this is a leading cause of death for ages 10 to 16, 24, although these days in Canada and also North America, these numbers are being matched by the opioid crisis. And nevertheless, it's an important objective to reduce these cases. There is obviously also very specific benefits that actually drive the economy, right? In the sense that we can dream about the comfort and convenience of maybe sleeping in a car that can drive us at night, and we wouldn't have to worry about safety issues, or the tracking that could be done at night when the roads are maybe most empty, improved mobility, traffic optimization, and perhaps in future even redesigning the cities, like repurposing parking lots and so on, right? So there are big potentials that could be realized, but we are still, as you will see during this talk, we are still quite far from it. All right, so how does this work? Well, driving is a very complex task, particularly if we think about like an urban environment. This is downtown Toronto, where there's just a lot of things going on, and not everything is relevant to the decisions that are being taken, but a lot can happen, and all of these things have to be sort of on the radar screen, have to be part of the situation awareness of the system. And then optimal decisions have to be taken. And particularly if we imagine these systems sharing a road with human road users, that becomes extremely tricky. So driving has a challenging environment. On the one hand side, we have physics. Well, that we have a pretty good handle on, but we have to deal also with this socio-technical system, basically the traffic rules, but also the culture around. I mean, things that are rules that are unwritten that will differ from city to city or from country to country. And the world that we operate these robots in is open world, meaning it's a natural environment that anything can happen. You can have animals running on the road. You can have rocks or tree branches and sort of unexpected things happening, right? And we kind of have to take care of all of that and make the system safe enough, right? And the idea here is that even if we now introduced a system into the such a self-driving system into the traffic, this will have to be an evolution, and we will have to have a coexistence of human-driven vehicles and automated vehicles. But even after all vehicles are automated, and that will be easiest for realizing some of the benefits, as I was saying, for example, traffic control, and optimizing the traffic flow and the fuel economy, or let's say energy consumption and so on. All of these benefits would be best, of course, in that final scenario. But even then, we're going to have human road users like pedestrians, cyclists, that we have to take care of and interact with. So I've spent some time thinking about this environment, and essentially, if we're building systems like that, we really want to also have some way of thinking about the requirements. Like what should the systems adhere to? What are the requirements in terms of both functional requirements and quality requirements and non-functional requirements? So as part of that, I've spent 1.5 years developing a framework that sort of allows you to think about the automated driving system as part of a vehicle that's being controlled. And the requirements are really a contract between that vehicle and its road environment in terms of how that vehicle should be behaving in the road environment. And this contract has various elements. Well, first of all, there's a whole ontology of elements that need to be perceived by the system, and there is a set of qualities we have to take into account, like obviously safety, comfort, progress, energy efficiency, and also sort of fitting into the flow of traffic, or you could call it courtesy, sort of the vehicle being predictable but also cultured and understandable of other road users, particularly human road users, and all of these different qualities have to be realized through a set of tasks that occur at different levels of abstraction. And so we have some insights into what these tasks are from studying human driving. So this is an example model of human driver behavior from John Michon, which essentially divides it into these 3 levels that occur at different levels of time and spatial scale or abstraction. So at the highest level, we have the strategic level where we make decisions about which roads we take, how do we get to our destination. So it's essentially the whole trip is being considered. But then at some point, at each point during the trip, we have to make very specific individual decisions. We come to an intersection at a traffic stop sign, for example. We have to stop and yield to other vehicles. These are maneuvers, and they occur at sort of second level. And then all of that has to be then performed into precise movements on the road, which are on the order of milliseconds and in centimeter accuracy. And so these tasks are subject to these very important qualities like safety, which is essentially the idea that we have to, risk that needs to be maintained to a acceptable level. That's basically what safety is. Even establishing what acceptable level is a challenge. It's challenging for human drivers, and it's the more challenging when we put such expectations to robots. But in general, risk is a combination of severity of the outcomes and the likelihood. And for driving, there is very specific events we want to avoid. There are collisions and non-collision events that we want to avoid. And we want to do this through a variety of rules. And I will sort of step through some of these things just very quickly, given the time here. But essentially, there's sort of the physics level challenges of just maintaining vehicle stability and not bumping into things, all the way to essentially obeying traffic rules, but also understanding the behavior of other road users and being sort of proactive in how we do the safety. I kind of like to kind of divide this into these 4 quadrants, and so essentially classifying the safety. And I classify behavior safety into sort of the proactive and reactive level and basic and extra. So the basic level of safety is, the reactive one is just avoiding crash by essentially not bumping into things, right? But in traffic, we want to also be a bit more foreseeing what's going to happen, what others will be doing. For example, applying safe distance, foreseeing that someone is perhaps doing, we observe some erratic driving, and so that's what I call proactive driving. And so there's a certain level that is very basic, and this is basically what maybe it's described in formal traffic rules. And there's also what I call extra safety. These are the things that, let's say, professional drivers, or when you do, like for example, professional driver training, these are the kind of heuristics that you learn, right? And so a lot of these aspects apply to automated driving too. And the idea is that whatever robot we build in the end will have to be imparted these type of safety model or safety thinking has to be realized. All right, so I've written up these aspects of these requirements. If someone is interested, it's published. But it's sort of now taking that and trying to boil this down for a robot. Essentially, what it means is that at a high level, we might say we've got a bunch of rules that we need to adhere to, like let's say traffic rules. But then there's also these qualities. So it turns out really that all of that it's essentially these are kind of cost functions. So even something like a traffic rule, if you think about running the stop sign, it's like, okay, did I stop for 1 second, for 3 seconds, for did I slow down? How many stop signs did I run? Like in the end, these things become quantitative, and so we can really capture all of these aspects, all of these requirements as in essence, sort of scoring rules, right? Or you can think of it as quantitative cost functions or scoring rules, right? And they are, according to sort of the structure that I just described to you, they can be organized into a DAG like this, a hierarchy of importance, where clearly some rules are more important than others, and there's some that maybe they're kind of incomparable. So in fact, this formally it's a pre-order hierarchy, but roughly what it means that there's we have to consider safety of humans, safety of the property, operational limits, then the physical interaction. So in terms of the traffic rules, for example, also, but then also the things like passenger comfort, and there could be also how the sort of driving style, or how the courtesy, how the vehicle behaves in traffic. So that is something that needs to be maintained explicitly. And I believe this is something that in future, if we have these systems on the road, some of these things will have to be standardized, particularly the safety ones across different systems. Some of that will be differentiating within companies, but this will have to be explicit, has to be connected to human values, something I will come back to later. But okay, let's sort of switch gears here and talk a little bit more about, once we know what the requirements are, how do we build such things? So what does it take to drive a car? We need to perceive the environment, we need to make decisions, and we need to execute these decisions by steering and braking and throttle. And so what I'm going to briefly describe here is a kind of sequence of different ideas for how such systems can be realized. That's very much inspired by thinking from Raquel Utasun from U of T, and well, she used to lead the UBA ATG as a chief scientist, and she's been just doing amazing work there. And I'll be actually bringing up a couple of ideas from her work in here, right? So okay, so the sort of three kind of generations of three types of architectures to build such systems are shown here on the slide. And essentially, the idea is that we can either kind of go for something what's called monolithic neural network, where essentially we take a neural network and just, for example, in a supervised fashion, feed it on one side with sensors, and then and supervise it with what the outcome should be. So essentially train it with what the driver would do. And that's one possibility. Another possibility is to build up the system with many of the wonderful works that have been done in robotics over the decades, in terms of how do you build individual systems like detectors, trackers, prediction planners, controllers, and so on, right? And sort of build this modular system. But where the future is going, and one can see this clearly now in the literature, that you kind of have a combination of the two, in the sense that this kind of modular classical algorithm architectures are being piece by piece more replaced by learned versions, often neural networks, deep neural networks, to kind of give you a hybrid solution. But that solution is even more and more just becoming what you could call a modular neural network, right? Or a system that can be optimized end to end. And so sort of that's how I see the work that's being published these days. This is where the direction is going. And I'm just gonna go quickly again through these each of these types of architectures. So this idea of the monolithic neural network, it's actually pretty old. It's quite interesting that this is going back to 1995 at CMU. There was a prototype that was demonstrated by Dan Pomerleau, who essentially had a van with a computer in it and a camera, and and a LiDAR, and he essentially would feed the camera image, the individual frames, and the rangefinder through a fairly simple feed-forward neural network that had 45 output units and just 29 hidden units. And these outputs were essentially representing what direction should the steering wheel be pointing. And so essentially he demonstrated kind of road following functionality using this system. So this was one of the first sort of end-to-end systems. So this type of architecture is fairly popular these days in research. And there's also some startups that try to do things like small sidewalk delivery robots using this type of technology. Well, one key thing is that this doesn't really scale in terms of safety, right? Because the trouble is that it requires an exponential amount of data to train compared to a modular approach. So, for example, if I want to improve just, let's say, detection and tracking, I can have a dedicated network for that, and I would have exponentially less data needed to get the same training signal or the same also quality that comes out compared to a system that I put that tracking, detection tracking together with planning, and I'll try to train it end to end. That will need exponentially more data. And if you're interested, there's the arguments for that I've written in this paper. Well, I guess I should mention one more thing, that this is actually kind of the architecture that's used by the Open Pilot. And so that's an open source project, and supports currently, I think, something like 50 cars. And so you can take, for example, one of the latest Toyotas or Ford vehicles, and you can essentially add a device. Originally, this was working on a smartphone. Now there's a dedicated hardware, and there's a link, and you can essentially add something like a Tesla Autopilot to your newest model that doesn't have one, right? And it essentially uses this approach. All right, then the kind of more traditional approach is this sort of classical modular architecture, which came out of the DARPA challenges. And this is what essentially in the end went into the self-driving car from Google. And that architecture is also pretty much what we've done in Waterloo here with the Wave Lab with somewhat over 2.5 years. We went from essentially just getting a car with sensors and steer-by-wire to building the software, which was that type of modular software in terms of having separate detector, object detector, having a tracker, occupancy grid that's LiDAR based, localization module, and then behavior planner, local planner, that then in the end feeds into vehicle controller. And so let me just kind of step you through this briefly, what such a stack does. So we take in sensor and maps, so sensor data and map data. So in our case, we were using the front view camera and 360-degree LiDAR scans. we would also use a high definition map. And that's a fairly standard thing, meaning that pretty much all of these self-driving cars today, or these prototypes, well, including the Waymo car, they all use high definition maps, rely on them. They will be confirmed, but you can think of these maps as sort of like the memory that a human driver would have going to a place and being familiar with, okay, this is the intersection that I've seen before. You know, I have to be careful here at this corner, and this is what comes after this corner. This is what a map then actually represents for this type of car. It's sort of this memory of the location. It has to confirm it because the environment is changing, but in essence, this high definition map is sort of like what you have in your GPS system, except that it has a very precise representation of lanes, and we can kind of see it, well, particularly at intersections when the lanes are connecting. We essentially have the information where is the center of the lane, so we can bias the car to drive, for example, on this center of the lane. Then the next thing is we need to detect objects that are relevant for driving, such as other vehicles, pedestrians and cyclists. And we have to estimate the time and essentially string these detections over time and understand at what speed they are going, whether they're accelerating, decelerating. We call these tracks. And we also have to predict them into future. Like in our system, we use a very simple prediction, essentially taking the velocity vector and linearly projecting it for the next 3 seconds. In these type of stacks, you would normally have a more sophisticated prediction system that takes into account, for example, the road geometry and also the behavior of other road users. And then finally, we would feed these predictions into the so-called behavior planner, which is essentially deciding what maneuvers should be executed at each step. And in our system, we use essentially, if you want, like an old style declarative AI system, an expert system, which is rule-based, where all the traffic rules are explicitly written. And then once, for example, the decision is to continue at the current speed or decelerate to stop or make a turn, then the trajectory planner would plan smooth trajectories that then are executed by the controller. And so with that approach, we've been able to demonstrate 100-kilometer driving in Waterloo. This was back in 2018. It was something that we celebrated back then with the team. And so here's Professor Woslander, this is myself, and this is the wonderful, amazing team of students, postdocs, research engineers. We also have here Professor Fischmeister. So it was quite a feat for University of Waterloo. And this was the first Canadian built car or software that was actually tested in autonomous mode on Canadian public roads. All right, so that's the first generation engineering stack. So it's highly modular, has clear interfaces. Each module is developed independently. That's how we organized our development. We had essentially teams for doing detection tracking, for doing mapping, for doing planning, control, and then simulation, vehicle integration, and so on. And they're also very clearly defined interfaces, and they're very thin interfaces. So like, let's say in this case, we have point clouds and individual images that come in. Here we have bounding boxes. Here we have tracks, which are kind of, you can think of it as like a sequences of bounding boxes, but they are with ID. So, and then we're also with state estimates in terms of the velocity and acceleration and so on. And then let's say that's what comes in here. Then here is essentially the individual maneuvers, like decelerate to stop, or continue at current speed, or yield, or overtake, things like that. And so these are kind of bottlenecks in the information, right? So, but it makes it very nice in terms of understanding, let's say if a team that does tracking, if they agree with the team that does detection on this very clear interface with how we represent bounding boxes, then they can go off and implement that interdependently. But we did see also the challenges. And so one of the challenges that we've seen is that, for example, changes in we would have improvements in maybe tracking, right, or detection in tracking, but then we would run into the problem that, for example, Frederick Bouchard, who's developing the behavior planner, he actually had compensation code in the behavior planner for certain types of mistakes that the perception system would been doing. For example, in velocity estimation, and then we would have an improvement here, but then the improvement did not really translate into improvement of the overall system right away. And so we had to, for example, then go and adjust the rules in the behavior planner to take advantage of whatever was improved in perception. And so this is something that Raquel Utazun points out has been experienced also at other companies like at Uber, for example, ATG, and that's it's something that slows down the overall process enormously. So the ideal thing would be to actually be able to optimize such a system end to end, such that improvements that you make, let's say in perception, automatically, the rest of the system learns to take advantage of them, right? So that's a powerful idea that I think future systems will have to exploit. The other challenge in using neural networks, and in our case it was mainly for detection, is the lack of reliability and robustness, and that's and I'm going to come back to this topic. Today's deep learning can be described as sort of system one technology, and so this is terminology from Daniel Kahneman, who says that like human mind roughly has the system one, which is sort of unconscious, automatic, and system one, which is conscious, where the reasoning is done, where you can explain things, what you're doing, whereas this is sort of automatic, and this is how we recognize faces, for example. This is how we drive 99% maybe of the time, but then when we get into difficult situations, we need to fall back into the reasoning part, right? And so, like one way to maybe describe how deep learning today works, it's like a super sharp colleague. In fact, there've been so many examples where deep learning was shown to have superhuman capabilities, but then it just fails in such laughable ways sometimes. So it's like a super sharp colleague that may be not totally reliable. And so the question is, do you want such an agent driving your car, right? And would you like to submit your life to such a driver, right? All right. The other challenges with the small rigid interfaces is, let's say if we detect, we have bounding boxes and then we have tracker. In fact, in order to, so in our system, we were mostly aligning detections into tracks by predicting where they would be and by geometry. You can do a better job, of course, when you start extracting appearance features from these objects and then aligning those. And in fact, what you really want is you want much more information to flow through the system, right? So, for example, yes, for tracking, you want more than just bounding boxes. And when you do prediction, there's lots of cues that, for example, a human would use to understand what another agent would be doing. Like, for example, what a pedestrian would do in terms of whether the pedestrian will be stepping on the road and crossing the road, or whether it will be yielding. So to recognize this type of intention, you need much more than just bounding boxes. And so, this sort of first generation engineering stack, in essence, you can think of it as like trying to drive in the world of bounding boxes where you don't see more detail than just that. And that's clearly very limiting. And so the challenge is, of course, now, well, how much more information do I need on these interfaces? And in fact, this the same kind of challenge that has been addressed in computer vision when we were trying to develop models that would recognize faces, recognize natural objects. And so the initial attempt was to actually handcraft these features, and that has pretty much failed. And only with with deep learning, where we actually started learning these features from data, it had become possible to recognize these objects. And I believe this is the same kind of idea here, that really this the information that's here should be learned and optimized from essentially from data. All right, and so let's move on to this envisioned system that basically says, okay, well, let's have each of these modules essentially learnable, allow them to have wide interfaces, but also at the same time allow supervision, or at least allow representations that are interpretable. So yes, I want to not just kind of go in a monolithic fashion from sensor data to outputs, but I want to see, well, what were the detections? What were the trajectories? What were the maneuvers? What were the planned trajectories, right? And perhaps even have a way to get some insight into maybe what are the learned features. So certainly we can provide some priors, some constraints over what like that. For example, that intermediate representation, I should be able to recover from that, maybe latent representation. I should be able to recover the detections, but maybe there's more information, just the detections. Maybe there are individual features that would be relevant down, maybe when we actually look into trajectories or prediction. And so one would like to be able to actually go back to meaningful representations, explain these representations to human engineers, because in the end, we want to build such systems in a way that the engineers have intellectual control over the system that they're building. So like end-to-end black box neural networks is not going to do it. And so, there are very interesting works in this direction, where, of course, we can use things like encoders, decoders. We can try to bias the latent representations, but also try to see what type of features are being learned. And this is something that is very much these days current research, cutting edge, and not something that we really know yet how to do well. So I'm just mentioning here that some of these ideas have been realized in the group by Raquel, and so I'm putting some of the papers. There's many more that have been incredibly productive in that space. Now, but I think that one important aspect is, like in most of the work that I've seen in this space is sort of assumes that this whole stack is being trained, like in the end, in supervised fashion. It is, what we call imitation learning, right? So even if you supervise some of the intermediate things, in the end, it just basically, the data is coming from observing the data in the field, like collected, let's say, by a fleet of vehicles, for example. And the fundamental limitation of that is that in this open world, there's obviously a very long, heavy tail of possible events that you will see only rarely, but when they happen, bad things happen, like accidents. And you don't want that to happen in practice. You want to be able to discover these things, experience these things early on in development. And so I believe that really one important thing is to actually have more explainable, interpretable models of behavior, particularly human behavior, because we are interacting with other world users. And so I don't think it's enough to just train these systems in a supervised fashion or as imitation learning. So, what can you do? Well, I mean, you can do explainable policies, handcrafted, just as we did it in the Autonomoose project. But that's ultimately very brittle and also limited in terms of what you can do. I mean, our vehicle has been extremely cautious. You would get to let's say, unsignalized intersection and wait for everyone else to leave before it would go, because we would be basically afraid to play a game of yield and take priority. which humans are great at. And doing this with robots, it's a tricky business. So yeah, we can do things like reinforcement learning, and I will very briefly just talk about that. So with reinforcement learning, there've been amazing results in games like AlphaGo and subsequent feats, and things like in robotics, like a robot motion. The thing that you will see is that for these successes to be possible, you had to have essentially an environment that's well defined, that basically has like the reward function, the notion of what it means to win the game, that's well defined, and everything in terms of the agents, the whole environment is just well defined. And then the system plays against, it's a essentially single player game, plays against the environment or within the environment. And in driving, it's not like that, right? In driving, we have multi-agent interaction. Each agent has its own, if we had a rational view of it, would have its own cost functions or rewards. Many agents are actually not, like humans are in general, not rational agents. So we need to consider bounded rationality. And in general, we don't have precise models of how humans behave. So a lot of studies have been done in economics, but that's sort of the rational long-term behavior. In traffic, we kind of have a mix of what humans do sort of at the strategic level, the trip level, that's rational. But the things that happen on tactical level and operational level, the second and sub-second, they're often automatic, but with different style and different sort of optimization criteria and different limitations for different humans. And so that makes it really difficult to just discover these problems, these heavy tail events just from data. So basically, I believe that actually using game theory is super important, because we want to build models that actually give us understanding of how such systems, what are the dynamics of these systems, of interactions between different agents. Also, if you introduce certain behaviors, what does it mean for the whole system? And we will be facing that when introducing robots into our traffic, right? So I think I'm gonna have to speed up some of these, because there's only a few minutes left. So reinforcement learning, I'm going to say what it is, and then like what the limitations are. So in reinforcement learning, we have an agent that is essentially maximizing its utility or expected utility. And this is what it does in terms of then deciding what is the optimal action to do, right? And it then observe what is happening, computes its reward, and this is how it learns, basically from signals from these rewards. It learns how to interact and by maximizing the expected reward, behave optimally, right? We've done some work because we thought this would be really cool and to basically learn how to drive via reinforcement learning. And so a whole team here listed. We've done some, we've built an environment where you can actually play with different scenarios and learn policies. But without going into detail, the general assessment is that reinforcement learning has a very high, what we say, sample complexity, which means it just needs a lot of training to discover things that sometimes from direct supervision or from imitation learning you can have very quickly. You don't need to go to these pains, so to speak. It's tricky to get it to converge, and actually defining reward functions such that actually makes these agents learn is very difficult. So you often end up tweaking this, how much penalty you give for a crash versus how much reward you give for not getting stuck and moving forward, right? And so that has been quite a disappointment in a sense, right? And it still results in far too high failure rate. The policies that we learned that that we not possibly could even test it on, let's say, on the full vehicle. And there is no theoretical guarantees really for so-called safe RL. There's lots of research, and it's really just called, I would put it, the so-called safe RL research. It's safe in quotation marks. It doesn't even provide. So the papers are being published are basically about maybe reducing some risk, but they cannot even give probabilistic guarantees today, right? So there's nothing about safety there. Okay, let's and well, I guess the other thing is that if you want to have RL, well, you have to have a simulator where you can train it, and simulator is not the real world. And if you had a simulator that's acting like a real world, you would have figured the self-driving is in the first place, right? So that's the problem. I think Nanoscopic. Well, okay, so traffic games, basically game theory applied to traffic, and not at the level of routing, but at the level of maneuvers and planning, right? So at the sort of nanoscopic level, it's an extremely useful tool to build models that can be then fed with data, where the parameters can be set by data, but we can very deliberately induce errors and limitations to behavior of road users. We can induce behaviors such as distracted driving. We can induce, let's say, the aggressive driver and the overly cautious driver. We can have a driver that maybe regards certain rules. And I think this is an extremely useful tool to actually build simulation that will be allowing us to discover those long tails and also build much better planners. And I don't have time much to go into detail of it, but in general, these games are hierarchical because we have to talk about maneuvers. Sometimes that can be even divided into multiple hierarchies down to trajectories. There are general sum games, so they're not zero sum games. We have different, they're multi-objective in the sense that we have sort of negative and positive rewards or costs. We call them inhibitory, excitatory, and we can link this to traffic psychology. We have partial and noisy observations, and we have heterogeneous agent population where the robots are rational, and where the human road users use various forms of bounded rationality. And like the interactions, like it's very nice to think about. Let's say something like a roundabout, and I live close by to a roundabout, and whenever I drive through that, and it's often very, very busy, and I'm always horrified, particularly in busy traffic, and I see so many folks making dangerous moves on this roundabout, and always you have to kind of watch out who is coming. Is this an aggressive driver? Will this person let me in? And it's a split-second decision, right? So and this is the kind of situations you can actually analyze using game theory. I just want to highlight this work with Patricia Sarkar, one of my PhD students, where we actually took, we collected traffic data in Waterloo at multiple locations where we have sent this to a company to have these trajectories annotated, and so we can study these games. And so these games are multiplayer games. There are multiple overlapping games, simultaneous games that are happening. They are hierarchical games, and we can actually build models of those and try to fit them into data, and then study which solution concepts from game theory are perhaps predicting the behaviors that we see best. And so we can think about different types of solution games like sampling equilibria, where maybe the sampling is what's bounds the sort of the range of possibilities that a human maybe can consider as a human driver. You don't think about every possible move of everyone else, but you're doing certain sampling of reasonable number of major possible maneuvers of everyone else, or maybe of those vehicles that are actually relevant to you, because again, these are multiple games simultaneous that are overlapping that go on. And we in this work, we've actually looked at 28 different solution concepts and got some initial insights in which of those solution concepts explain the behavior best. But the bottom line is that different solution concepts will apply to different types of situations. And there's lots that we can still learn about. And a lot of this work on behavioral game theory has been done in economics. And I think that the applying it to sort of this short range thinking that we see in traffic is a very fruitful and relatively new area to explore. All right, so I think that this is a great direction, but in terms of learning, I don't think supervised learning alone cuts it, and I don't think that just learning from data alone without thinking about the models, for example, models of behavior, will be enough. So I believe integrating this type of vision with this concept I was just describing will be the future direction. And so I do think that reinforcement learning will play a role, but perhaps not in this pure fashion that we have today. We definitely have to think about much richer reward structures, because as I showed you at the beginning of the talk, the requirement structure is this whole very complex directed acyclic graph with the different groups of scoring rules with different priorities and optimizing within that space. It's a fairly complex problem. It requires counterfactual reasoning. Certainly, some forms of meta learning will be important, and imitation learning will, of course, be part of that, because there is no point in rediscovering, so to speak, the obvious rules of driving a behavior that you can just simply observe and learn from. All right, so let me start wrapping up here. So the question is, where are we today with this technology? So I'm showing here progress that's been done by Waymo, and Waymo, by the way, is the absolutely top leading technology in this space in the world. They were the first one to start. They had an amazing engineering team and amazing resources, and they're simply ahead of everyone else, period. Right? I mean, maybe the second closing on is Cruise, but even then they are way behind. And so this shows here how Waymo has progressed over the years from 2015 to 2020. So in California, there are these so-called disengagement reports that are mandatory for self-driving companies who test on the road, and they have to report so-called disengagements. So now, what is a disengagement? That is an interesting question. There are many possibilities, and in fact, sadly, this differs from company to company. But Waymo has been, and Google has been, fairly consistent and also transparent in describing what they consider a disengagement, and that's all described in the reports. The disengagements that are being reported are mainly the safety ones, so those that prevent accidents, and also those from so-called precautionary. So this is where a driver takes over because thinks that this is maybe not such a good situation, but then that needs to be confirmed in simulation where this was actually a safety, whether this situation with the software would have led to an accident down the road. And so these safety-related ones, so this would be the miles driven between disengagements. So back in 2015, essentially every 1,500 miles, there would be such a disengagement, a safety incident. And in California, in last year, it was an average every 30,000 miles. And you see, this is an incredible improvement over the years. Now, as I said, there's really only Waymo who now has a service in terms of actually running these things without a driver as a product. So today, if there wasn't COVID, I would just fly down to Arizona. I would have got the app on my phone, and then and I would definitely take a ride. I would love to do that. And General public can do this now. And they actually, they charge for it. So it's an actual commercial service. They don't make any money on that. And I think it's going to take quite some time for anyone to make money on it. But it's impressive that they open it up to the public. So, and the statistics from there are somewhat different. They probably don't use exactly the same criteria as in California, but in Chandler, it's 130,000 miles between contact incidents. So this is now slightly more serious, where you actually had a bump between cars. And it turns out that all of them so far have been faults of others. But to be fair, a human driver might have prevented them, right? So it can be still a limitation of this technology, right? And also, this is all in perfect driving conditions, where you have grid marking, lane marking, and weather, and it's suburban traffic rather than, let's say like Toronto downtown, right? And just for comparison, what humans do, so roughly you have every 100,000 miles, you have some incident, maybe not reported. If it's insurance reported, it's every 250,000, and police reported every 500,000 miles. And you have fatal or crash roughly every 100,000 miles. And so but the difference, so let's say when you look at this, is sort of approaching it. So it's quite impressive, right? I think it's incredibly impressive. But the big difference is that this is in these conditions, and these statistics are across a full range of driving conditions, right? In all the weathers and complex environments that humans drive today, right? So I think we still have a long way to go. And we can see this because even between 2014 and 17, there've been $80 billion invested. But the progress has been such that all these companies, including Cruise, have been just delaying introduction of their products by year for year, basically. And like recently, Uber even just sold ATG because they didn't feel like paying these billions to pay these engineers for another 5 years, or who knows how long, right? All right, so wrapping up, the key challenges are achieving superhuman performance. That's still very difficult. AI, how do I assure that these things don't fail when they see out of distribution or edge cases, if you want? And predicting what other humans will do, that's extremely challenging. Again, and these are all these hazard sources that I don't have time to go. There's a lot of things can go wrong with these systems. Where are we going? Well, I think in the long term, really the progress in AI will be necessary, and in what I call here System 2 AI technology, to address, for example, out of distribution cases, and then to be able to assure these methods, particularly with AI, and have better models of human behavior. And so just kind of to say what I mean by System 2 is that, the current deep learning is this unconscious thing that, recognizes faces, right? Let's say it recognizes objects and, maybe movements and so on, but it cannot really reason. And so when it's faced with something new, it's like in driving, if the 99% of driving, I can drive and relax and have a conversation. But once you get into some more tricky situation, like the roundabout, if someone was talking to me, I would say, no, stop, because if I start engaging in talking, there will be an accident, right? Essentially. So, and that's where the future AI will have to address that. I mean, there's work now that starts to think about how to get reasoning on top of sort of semantic reasoning on top of deep learning, and that's quite exciting. And I think I really have to stop. We have to also make it human-centered. So, the requirements I was talking about has to start with human values, and has to define how these robots behave in traffic. So I think that's also another super important future direction. So this is some of the research that we do. Like, I can leave it for questions, but let me just stop here and see what questions we have.
Hi, Krzysztof. So we have 3 questions. Can you hear me okay?
Yep, very good.
Okay, wonderful. So the first question, there's a question about the sensing capability of autonomous vehicles. So basically, what impacts the accuracy of sensors is the first part of the question. And the second part is, does a mapping relationship exist between the distance of the object and detection accuracy?
Okay, let me see. So it's the first one, the first one was
what is the
Yep.
Sorry, the first part was what impacts the accuracy of sensors?
Right. So, well, several things. I mean, the accuracy of the sensors is impacted by, first of all, the characteristics of the sensor itself. This starts with, like, when we take a camera will have limitations, let's say at night, based on the illumination. It will have limitations in terms of like atmospheric pollution or precipitation. LiDAR will have very similar in terms of the visibility, what you have in the atmosphere, but for example, it's not impacted by lighting, right? Because it has its own source of light, infrared. And so if you take each of those sensors and then radar, there will be characteristics, first of all, just what the wavelength is doing, and what type of quality of sensor was deployed into vehicle. And this is something that's being improved all the time. Like, for example, Waymo has its own LiDAR that's manufactured designed and manufactured for Waymo specifically. For example, they can have even like the size of particles that intercept the beams are being measured. I think in terms of like future development, what I find super exciting is this idea of multispectral cameras and scanners, where rather than, for example, cameras have RGB, right, red, green, and blue, you can have a spectral camera that takes, for example, 128 measurements in terms of spectral frequencies. And with that, you can actually classify something like, let's say, like a human flesh or like skin or vegetation can be recognized right away from the signal from the camera without any deep learning. Or recognizing eyes, for example. You can do this at different infrared frequencies, right? So yes, I mean, conditions will influence the accuracy, but I think there's a lot of innovation that can still happen in sensors without improving, without even relying on deep learning to address these issues. And then the second part of the question was?
The second part of the question is, does a mapping relationship exist between the distance of the object and detection accuracy?
Oh, yes, absolutely. And so, like in our system, sadly, we had trouble detecting objects, like recognizing them beyond 40 meters. And although the LiDAR itself can do returns up to 100 meters, roughly, but then cars, there would be, let's say, a car, right? There would be, let's say, something like, 40, 50 meters. You might just get a handful of points on the car, right? So maybe like 5 points. And then, below 5 points, it's hard to recognize that this is actually a car. And if you have a small object like a pedestrian, this problem occurs much earlier. So therefore, if you let's say have high-speed driving, let's say on a highway, you actually do have to have special sensors that have a higher resolution in certain directions where it matters, right? So let's say you have to have a high resolution to recognize cars ahead, oncoming cars. Or if you're approaching, let's say, a signal light, your camera has to have enough pixels to see the red light from far enough, right? So yeah, definitely. All right.
Okay, so the next question, we do have a few. The next question is, for the Generation 2 stack, modular end-to-end, I suppose there are a wide spectrum of features to learn from, locations, decisions, etc. But what does the loss function look like? Just based on the action or also based on the intermediate features? If the latter...
Yeah, that's an excellent question. So, well, first of all, I think the loss function will have to be derived from this, big. Just kind of while talking, I just scroll it up from this big DAG that I was showing initially, right? So this obviously is the final thing you want, right? It's the various qualities of driving that needs to be. Let me see. I think I went too far here. Right here. So the loss functions, for the driving qualities, that's the starting point, right? But then remember that we want to be able to actually have insights into what the system does at intermediate levels. Why? Because if I just do this, this DAG in an end-to-end fashion, I need exponentially more data than if I actually start looking into intermediate nodes and say, oh, okay, you didn't do properly here a behavior because you didn't recognize this weird-looking car. But I want to even know that there is, it can recognize weird-looking car, even if it's maybe on the opposite lane. So maybe it didn't actually matter for this current situation. But if that car, possibly has driven in the same lane ahead, we would have had a problem, right? So I think so. That's gonna be definitely a complex set of loss functions, right? So the ultimately end-to-end question is this DAG. That's what we're optimizing, but we also have these intermediate representations to optimize A for the future unforeseen situations and B for the engineers to be able to control the system, to have this intellectual control over the system, right? Because I want to have these interpretable intermediate representations. So that's, yeah, I would answer this.
Okay, so the next question that we're going to go to is, and I hope I pronounced this correctly, is LiDAR necessary for level 4 automation, or does a camera suffice?
All right, so, I mean, this controversy is sort of this been constantly stirred by like Elon Musk or George Hotz, just because they are kind of, putting the bets on the cheapest possible solution that they put in the hardware and have it today, and promising that they're going to have self-driving cars. But the fact is that with cameras, although in theory and in practice, actually, yes, you can recognize 3D structure of the world, but you have all sorts of limitations. You have limitations at night, for example, that LiDAR can alleviate. And of course, you need radar because, and even Tesla does that because, yeah, you want to see through fog, right? Or in rainy conditions and so on. But LiDAR just gives you so much more extra information, and in a physically different sensing modality, right? You have a different light frequency in infrared that you add to a camera. And so that gives you additional sensing, plus also the fact that you measure distances directly. So you don't have to rely on sort of cues and recovering the distances from camera. That just adds so much more reliability to the system. It's sort of like if you look at in the natural world, I mean, like the different insects that see in different light frequencies and so on. And if we had, as humans, these possibilities, we would love to have that. And so we can do this for our robots. Why not do that, right? And like if I were to work on a safety case for a system, I'd be very suspicious if it claimed today that it can do all these things properly with just camera. I think that makes no sense. Right? Any next question?
Next question. Yep. How far into the future would we need to model the behavior of other road agents for safe autonomous driving? As an example, would modeling the behavior of humans for the next 10 seconds be enough?
Well, yeah, absolutely. Great question. Sort of in maneuvers, I think like up to 15 seconds, it's most of the maneuvers are kind of done within sort of 15 seconds. Some of the places where you need for longer, you may be at when you sort of stop in the intersection, and you can maybe observe some of the oncoming traffic for maybe a little longer, or the pedestrians, how they behave, waiting to cross. That might be useful, but I think sort of beyond maybe something like 15 seconds, it will be certainly diminishing. As a human, of course, there are cases where, let's say, I myself experience on let's say 401, where you see someone maybe sort of jumping from, changing lanes erratically from one to another, and you see them, sometimes you meet them more than once, right? And I would like to, right away profile and flag it as a dangerous driver, so to speak, right? And I think this type of capabilities should exist for autonomous vehicles too. Maybe those will be actually realized through, fleet communication. So, what I described was basically just for a single vehicle to make decisions, to be able to make decisions how we humans drive today, based on what we can see with our eyes. But with automated driving, we have this amazing possibility that the cars can actually share their observations among each other, and so one car can now start seeing spaces that will be occluded for it through the eyes of other cars. And so then maybe these situations where we need to have this longer observation, for example, saying, well, be careful around the corner. There is a weirdly behaving road user, and so you can be warned then, right? I think that there are endless possibilities, but at least 15 seconds, that would be quite useful.
Can you speak to any of the legal or liability hurdles that must be overcome before we will see widespread use of autonomous vehicles? For instance, if a fully autonomous vehicle injures a pedestrian, who is at fault?
Right. So, there's just some movement in various countries to develop some legal frameworks. This has multiple areas. So one of them is the legal in terms of liability, as raised here. The general approaches would be this even, let's say, for Canada is different. Within in Quebec versus rest of Canada, the liability for accidents, for example, is different, right? So except for Quebec, we have the common law, and Quebec is the civil law, sort of French-based. And so, for example, in Quebec, there is no fault insurance, meaning that if there is there's an accident, the victims would get compensated right away, and then any liability would be determined later in court, maybe passed on to manufacturer if it was a vehicle problem, or the driver if there was the operation, the driver here. And so some of these frameworks are being now extended, existing legal frameworks, to deal with autonomous vehicles. So, for example, in Germany, they introduced an amendment 2 years ago that allows driverless vehicles, those up to level 3 or level 4 in sort of parking lots, if you want, or parking garages. And the way they did this basically there is by requiring a much higher insurance for the vehicle owner. But it turns out that hasn't been satisfying, for example, the EU rules. And car makers like, for example, Audi, 2 years ago, they already had a product which they called traffic jam assist. It's a kind of stop and go system that you could, hands off in a traffic jam, you could basically completely relax, and it was a level 3 system that would completely take over responsibility. Not like, let's say, Tesla drive, a Tesla autopilot. The driver has a responsibility when the autopilot is engaged, but for that stop and go assist system from Audi, it would have been Audi responsible for the driving during that specific situation of traffic jam. And they, in the end, decided not to introduce it. They were just too afraid of the liabilities afforded by that legal framework that Germany introduced. So And it's a kind of double-edged sword because if you don't have the right legal framework, the manufacturers might be too timid, like let's say in the case of Germany, or you have companies like Tesla that might actually put on the market products that in some cases are not safe, right? So it's a very interesting challenge, right? I mean, down the road, I think I like this model of no fault insurance, and then the courts should be settling who is liable, whether it's the operator liable, whether it's the manufacturer liable, sort of like in let's say with airlines, right? I mean, you take a flight, and if there is any issues in that whole system, there's compensation, but then who is responsible? It should be taken care of, not with the casualties, right, or casualty families, right? But it should be taken out of that system. So, but I'm not a lawyer. I'm not. This is the kind of things I read and hear and think about. But these problems are not settled. Far from it. Okay. Well, any other questions?
Okay, so here's another one. Myself and others in the Autonomoose research group are exploring environment understanding for decision making via a relationship graph model that allows for both strong priors and learned posteriors. The idea of modular learning systems seems to have a similar goal to ours. Have you encountered literature that approaches scene understanding in such a modular learning fashion based on engineered relationship priors?
So, I guess some of the work that I was citing, by Raquel, but also there's several other works that looks at sort of interaction graphs and do this in a learned fashion. This is these priors are not somehow handcrafted. They are graph neural networks that would learn some features for the individual nodes and then look at pairwise relationships. I would say the most sort of kind of interactive hand-engineered prior is, for example, the work that I was citing from my PhD student Atrisha, where we built essentially these agents as in that game form, right? Where we consider some agents being rational, where we consider agents like humans with different, some of them would be using so-called quantal response. So basically, they kind of behave according to the utility they can get, but it's just with respect to the utility being like being like an exponentially proportional in terms of the probability of actually taking the decision that will give you that expected utility, right? There we were looking also at different types of behaviors in terms of cautious behaviors, where you kind of look at all possible maneuvers of others and say, well, with my action, I want to look at the worst possible outcomes and then take the best one that's left, right? And that's sort of a cautious driver. Or you can model someone who is more of a kind of aggressive driver, where you say, well, it's sort of hoping for the best case, right? And then you can look at the obviously rational behavior. And so yeah, with that, you can actually start model these things. Now, the challenge will be, of course, making these games solvable fast if you want to use it for planning. In our work, these games can be solved on the order of seconds. It's actually quite surprising. It's much better than maybe some of the economic games that's in the literature. But that can be sped up with learning, right? Because you can essentially learn these strategies that come from these equilibria, and then learn direct policies that could be then executed based on a given situation. But yeah, so I could recommend also looking at that. And most of the work that I see is these days in this space is when it's learned, it's sort of graph neural networks where there is no handcrafted expert knowledge being injected, really.
Can you briefly mention some of the attempts to bring the kind of more long-term semantic reasoning into deep learning?
So I recommend just reading this paper from Joshua Bengio. I hope this slides will be available somewhere. All right, here. So this paper here, and so yeah, this paper actually points to some also recent work by Joshua Bengio, where they kind of try to do sequential. They kind of wanna. It's almost like representing algorithms in deep learning, where rather than just having this sort of parallel input-output representation of a function, you actually have networks that are responsible for individual concepts, and then trying to learn how sequentially you can combine these ideas in a sort of algorithmic fashion. That's just one sort of element of that, and it sort of inspired how in system 2 people actually, you cannot, like, if you actually have to reason and also then explain what you do, you actually do things in a sequential fashion. That's why we cannot do multiple things at the same time that occupy our mental capacity, right? But essentially, yeah, I recommend this as a starting point.
Data usage and transfer is always vulnerable against security issues like hacking. How would you estimate the severity of this issue in autonomous driving?
Well, hugely, of course, because yeah, it's a system where if you hack into, you can do a lot of damage. I mean, some of the hacking that I've seen described in let's say research literature, kind of a bit unrealistic, like doing things like I don't know, putting stickers on traffic signs and so on. Like, I think there are easier ways to harm someone than that. But certainly, once you have connected cars and the ability to enter these systems while they're in operation and take over control, that's a huge risk. And these companies will have to all be super careful about that. The stakes are super high there, right? I mean, like, yeah, you can imagine all sorts of crazy things, like sending all cars into the ditch on a given day, and asking, pay me in Bitcoin so much, whatever. I mean, these kind of scenarios have to be prevented, right?
So maybe I will step in here because
probably over time, right?
Well, like the online format actually gives us the comfort that we can carry on, but I'm afraid that we will really exhaust you completely, and there's no end to the questions. So I encourage, of course, everybody to to reach out and contact you with questions if needed. But it was fantastic talk, and
just say that maybe like the question, Andrea, if possible, if you could maybe just save the questions that are there so I can follow up.
Yeah. Okay, they are actually with.
I will do so.
Yeah, with the names of participants. So it's a learning experience for us with this online seminars. But I thought it was really great, and looking forward to the next one. But we had like over half an hour discussion, or the questions and answers. So thank you very much, Krzysztof, once again for the fantastic seminar and for starting our series all together. And I was sort of surprised, but then not so much that it was your first ECE seminar since joining ECE. I'm sure there's many faculties in this situation here. I hope we'll be breaking this habit. Okay, so, and I would like to thank all the participants who are still hanging around for joining us for this session. And Andrea, thank you very much for taking the role of asking questions. I guess that's pretty much it for today.